Hello everyone, welcome to my channel. In this video, we will learn vectors, matrices, and arrays. Vectors, matrices, or arrays can only contain one type of data. For example, we cannot store both character and numeric data type in a vector, a matrix, or an array. The common properties for vectors are type, length, and vector attributes. We can store 4 common data types into a vector, including integer, double, logical, or character. Among these 4 types, the integer type is less commonly used, because we store numeric values into a vector as double most of the time. In the last video, we learned a simple way to create a vector by using the C function. In this video, we will learn other methods of creating vectors. In this example, my data vector is constructed by using the C function. We can use the type of function to find out its storage mode, and the length function to find out the number of elements in this vector. The class function tells us my data is a numeric vector. If we want to create a vector that only holds for integer values, we need to add the L suffix after integers within the C function. For example, the int vector is an integer vector that contains values of 1, 3, and 10. One of the reasons to store numbers in integer mode, instead of double, is to save storage space. Similar to creating a numeric vector, we can also create character or logical vectors by using the C function. The values that are used for the character vectors need to be enclosed in quotation marks. And values for logical vectors can be either true or false in the uppercase, or using uppercase T for true, and uppercase F for false. Once a vector is created, a common task is accessing the elements of a vector. One way to access elements of a vector is by enclosing the position numbers within a pair of square brackets. The first example returns the third element of my data, which is 4.5. To access a series of elements in the sequence, we can specify the beginning and ending indices within the square brackets and separate them by a colon. If the elements that we want to access are not in sequence, we can separate position indices by commas within the C function. We can add names to a vector by using the names function. For example, the letters vector is a built-in constant, containing letters from A to Z in lowercase. In this example, we assign lowercase letters from A to F as the names of my data. If a vector has names, we can use the names function to return the vector names. We can also access the vector elements by enclosing their names within the square brackets. The first example returns a vector element with names equaling A. We can group more than one name to access more than one element of a vector, like in the second example. The last example returns elements of my data with names equaling A to C.
Letters 1 to 3 returns lowercase a, b, and c. Since a, b, and c are the names of the first 3 elements of my data, enclosing letters 1 to 3 within the square brackets returns the first 3 elements of my data.
We can also create a vector and add its names by using name equals value format within the C function, like in this example. When a vector is assigned with names, we can say this vector has the names attribute. The names attribute is a standard attribute for a vector. Knowing what attributes an object has is essential to distinguish this object from other objects. In some situations, we might want to assign a user-defined or non-standard attribute to an object. To assign a user-defined attribute, we need to use the attr function. For example, we use the attr function to assign a new attribute, name new. The value for this new attribute is, this is a new attribute. The purpose of assigning a user-defined attribute might not be very clear for a beginner. We can consider this technique as a way of labeling an object in the program, and later in our program, we will be able to identify this object by using its unique attribute. Once an attribute is assigned to an object, we can access it by using the attr function. In the first example, we access the new attribute by using the attr function. We can use the attributes function to access all the attributes of an object. For example, v1 has 2 attributes, one is the names attribute, and the other is the one that we just created. Based on the printed result, we can see the value that is returned from the attributes function is a list object. Once a vector is created, we might need to add more components to an existing vector, which can be done by using the C function. For example, we add one element, which is 3.6, to my data. The second example combines two vectors together by using the C function. We can combine vectors with different data type. Since a vector can only contain one data type, the data type from the original vector will be coerced to another type during the concatenation. For example, when we combine a logical vector with an integer vector, the logical values will be converted to integers in the result. In this situation, the true value becomes 1, and the false value becomes 0. When we combine integers with double values, the result will be double values. If we combine a numeric vector with a character vector, numeric values will be converted to characters in the result. We can change the vector storage mode by using the functions that start with as. For example, as.character converts its argument to character, as.double converts its argument to double, etc. Arithmetical operations performed on vectors are done element by element. For example, when we add two vectors of the same length, the first element of the first vector will be added with the first element of the second vector, and the second element of the first vector will be added with the second element of the second vector, etc. In the situation when the lengths of the vectors are different, the shorter one is recycled during the calculation. For example, when we add vector A of length 2, with value 3, 3 will be added to each element of A because of the recycling rule. If the length of a longer vector is not a multiple of the shorter vector, R will issue a warning message, but it is not an error. This is generally not what we intended. In addition to use the C function to create a vector, we can use the colon operator to generate a sequence of numbers. The first example generates a sequence of numbers from 2 to 15. The second example generates a sequence of numbers from 10 to 1. The increment between each number by using the colon operator is either 1 or -1. A more flexible way to generate a sequence of numbers is to use the sec function. The first two arguments of the sec function, from and to, are used to specify the beginning and the end of the sequence. In this example, we generate a sequence of integers, from 2 to 10. The third and fourth arguments, by and length out, are used to specify a step size and the length of the sequence. These two arguments cannot be used at the same time. If the by argument is not given, the default value is 1. These two examples are equivalent. Both commands generate a sequence of numbers, from 2 to 20, with a step size equaling 3. Another useful function to generate a vector is rep function, which is to repeat an object. For example, the vector I is created by repeating 2, 4 times. The second example repeats vector x, which contains values 1 to 4, twice. The second argument of the rep function can be a vector with the same length as the first argument. In this situation, the repetition is done element by element. For example, x contains numbers 1 to 4. I contains 4 of the 2's.
Repeat x, I times means repeating each element of x twice. The second example repeats x times, which means repeating the first element of x once, the second element of x twice, the third element of x 3 times, and the fourth element of x 4 times.
In some applications, we might need to generate random numbers. All the random number generator functions start with the letter R. This example generates 100 random numbers, following a normal distribution, with means equaling 2, and standard deviation equaling 3. Since these generated numbers are random, every time we run the commands that contain a random number generator function, R will produce different patterns of numbers. Now let's see how to generate logical vectors. We can use the C function to create a logical vector. However, most of the time, a logical vector is generated from the comparison between two objects. To compare objects, we need to use the relational operators. For example, A is a numeric vector. Comparing whether A is greater than 2 generates a logical vector. Each element of the logical vector indicates whether it is greater than 2. The missing value will also result in a missing value after the comparison. One of the preliminary steps to process data is to examine whether it contains any missing values. To check whether a vector contains any missing values, we need to use the is.na function. A common mistake to check missing values is to compare a vector with na by using the double equals comparison operator. Since calculation or comparison that involved any missing values will result in missing values. Using the double equals comparison operator will generate a vector of NA, with the same length as the compared vector. The logical vectors are coerced into numeric vectors, in arithmetic calculations. In this case, true becomes 1 and false becomes 0. This example shows how to count the number of elements in a vector, greater than its average. First, the mean function returns the mean of vector g. In the second step, when we compare g with the mean of g, it returns a logical vector, with a length equal to the length of g. The true value indicates the current element is greater than its mean. In the final step, we use the sum function to count the number of elements in g, that is greater than the mean of g. During the calculation, since the true value becomes 1, and false becomes 0, the sum function results in 5. Here are two useful functions, that are often used with logical vectors. The any function returns true, if at least one element of a given vector is true. The all function returns true, if all the elements of a given vector are true. Instead of using any or all function, we can also solve the problems, based on what we've learned. For example, how to test if any elements in f equals 3.001. Since the any function returns one single true, or false value, we would like our alternative method to result in one single true, or false as well. There are 3 steps to accomplish this task. First, we need to compare f with 3.001, by using the double equal operator, which results in a vector of true, or false. In the second step, we can use the sum function, to count the number of elements in f equaling 3.001. The sum function returns 1 in this example. Lastly, we need to examine, if the result from the sum function is greater than 0. To examine whether two objects are equal, we often use a double equals comparison operator. The identical function can also be used to compare two objects. The difference between these two methods is that, the identical function only returns one single true or false value. But when we use a double equals or not equals operator, to compare two vectors with lengths greater than 1, we will not get a single true or false value. This example illustrates the differences. One useful function to work with logical vectors is the which function. The which function converts a logical vector to an integer representation. For example, h1 is a logical vector that is resulted by comparing vector h with value 5. We can use the which function to return the integer positions of the true values. A common operation for logical vectors is to combine or negate conditions by using the logical operators, such as single and, single or, and negation operators. The comparisons are performed element by element between vectors. These examples demonstrate the use of these logical operators. From the previous slide, z1 and z2 are the integer representation of h1 and h2. h1 and h2 operation is equivalent to, using the intersect function, applying to z1 and z2. h1 or h2 operation is equivalent to, using the union function for z1 and z2. The operation of h1 and not h2, is equivalent to the setDiff function for z1 and z2. R has a factor class for storing categorical data. A factor class is created on top of an integer vector, with two additional attributes, which are class and levels. To create a factor, we need to use the factor function. For example, county vector is a character vector, and county is a factor by converting county vector into a factor. The printed values from a factor are not in quotes, and each unique level of the factor is printed as well. Using the attributes function for a factor, return two attributes, one is levels, and the other is class. Since a factor is built on top of an integer vector, the internal storage mode is integer. The levels function returns the levels of a given factor, and n levels returns the number of levels. To convert a factor to a character, we can use the is.character function. Subsetting a factor is similar to subsetting a vector. For example, we can select the first three elements of a factor, by enclosing 1 to 3 within the square brackets. But one thing we need to be careful, when selecting elements from a factor. For example, after selecting the first three elements from the county factor, we have LA, SB, and LA. That means the returned value should only have two levels. But the printed result tells us, there are still 3 levels in the result. The n levels function further shows us that, there are 3 levels in county 1 factor. There are a couple of ways to eliminate the OC level. One way is to use the factor function again, after selecting the elements. Another way is to set drop option to true within the square brackets. A factor is stored as integer values. For example, in the county factor, LA is stored as 1, OC is stored as 2, and SB is stored as number 3. These values are assigned alphabetically. Some statistical functions, such as LM or GLM, give the first level of a factor a special status, such as treating it as the baseline level. The assigned first level might not be the one that we wanted. We can specify the levels explicitly by using the levels argument in the factor function when we create a factor. Like vectors, matrices and arrays can only contain one data type. A matrix is a special case of an array with only 2 dimensions, and an array has more than 2 dimensions. We can think about an array as a vector by adding the dim attribute. The dim attribute contains the dimension of an array. For example, we assign the dim attribute to my data vector, with 2 by 3 dimensions. Once a vector is converted to a matrix, or an array, its names attributes will be removed, because the names attributes is only available for an object that is linear. Another way to create a matrix is to use the matrix function. By default, a matrix is filled by column from a vector, by using the matrix function. If we want to fill the matrix by rows, we can set the by row argument to true in the matrix function. We can transpose a matrix by using the t function. After using the t function for my data, the resulting dimension becomes 3 by 2. We can combine matrices by columns, or by rows by using cbind, or our bind functions. In the first example, we combine my data with new data 1 by columns, by using the cbind function. The second example combines my data with new data 2 by rows, by using the rbind function. Since a matrix has 2 dimensions, we can assign row names and column names, by using the row names and col names functions. We can also use the dim names function, to assign row names and column names at the same time. We can use the length function, to find out the number of elements in a matrix. However, it is more meaningful to use nrow and ncol functions, to find out the number of rows and columns of a matrix. The attributes function shows us that my data matrix has the dim and the dim names attributes. To access one or more elements from a matrix, we need to enclose 2 indices, separated by a comma, within the square brackets. The first index refers to the row position, the second index refers to the column position. The first example accesses the element in the second row, and the third column, which is 2.4. If we leave one index position empty, that means all the elements will be included. The second example accesses the entire elements from the second row, since the position for the column index is left empty. Similarly, the last example accesses the third column. We can think about a vector as a one-dimensional array of numbers, and a matrix as a two-dimensional array. Arrays are multiple-way extensions of matrices, with more than 2 dimensions. To access the elements of a 3-dimensional array, we need to provide 3 indices. The first one refers to rows, the second one refers to columns, and the last one refers to pages, or the third dimension. For example, x is a vector of length 12. Assigning the dim attribute to x, with values of 2 by 2 by 3, changes x to a 3-dimensional array. We can assign row names, column names, and page names by using the dim names function. Here are the attributes of an array. Notice that they are the same as the ones from a matrix, including dim and dim names attributes. Alternatively, we can use the array function to create an array. The first argument of the array function is a vector to fill the array. The second argument is the dim attribute of the array. Now, let's talk about the null value. The null value is a special object, to indicate or specify an object is absent. The null object is not a vector of 0 length. It has no type, and no other modifiable properties. We cannot set attributes to null either. To check whether an object is null, we can use the is.null function. Now, let's review what we've learned from this video. In this video, we learned how to create vectors, matrices, and arrays by using different functions. we saw some examples of using vectors for calculations and comparisons. In some situations, a vector needs to be coerced from one type to the other, by following the rules of coercion. We also learned how to create and access the attributes of an object. Once objects are created, we often need to subset them, or combine them into a new object. Please like and subscribe to my channel, and click the bell icon to get new video updates.